Question number 3. I've got my 10 kilogram parcel. I've got my 50 meter cliff. And I remember that if I dropped it off, I conserved energy. And I found that V final was equal to 32 meters per second. But in this situation, we're starting with V naught is equal to 32 meters per second. And the different scenarios for A and B, the initial velocity is down. For C, the initial velocity is up. And for D, the initial velocity is horizontal. The easiest way to solve all of these is the same. We can see this is an energy problem because I know the mass, I know I can find the initial kinetic energy and potential energy, and I want to find the final velocity. So I can just say E final is equal to E naught, and that's all kinetic energy right before it hits the ground, 1/2 mv final squared is equal to mgh naught plus 1/2 mv naught squared. I like it because the masses cancel, and I wind up with V final is equal to 2gh naught plus V naught squared square root. But we can actually go back and say, hey, this kinetic energy at 32 meters per second is what it got when it dropped off here from rest. So this is actually equal to mgh. And I'm sure if you found the height shooting it up at 32 meters per second, you found that it went up to 100 meters. So this problem boils down to just saying if the potential energy, if the total energy, if energy goes to 2 times the initial energy, and it's all changed to kinetic energy, velocity goes to what? Like, how much do you increase the velocity? And you say, oh yeah, it goes to 2 times V naught, and then like, oh no, hold on, because kinetic energy is 1/2 mv squared. So if you multiply velocity by 2, you're going to multiply the energy by 4. And so, right, it must be 2 squared, which is 4. So, no, if you put 4 in there, you get 16. No, this is square root of 2. And so, the final velocity must equal the square root of 2 times 32 meters per second. Square root of 2 is like 1.4. So we're looking at 32 plus 12 or 13. So that's going to be like 45 meters per second. And that's the answer for all of these. They all start with the same kinetic energy. They all start with the same potential energy. They're all going to finish with the same kinetic energy. These two are going to hit right here, going straight down. This one is going to hit at some angle. The horizontal velocity will still be 32 meters per second because there's no force acting on it in this direction. There'll be no acceleration. And it'll have a downward velocity of 32 meters per second. And you can find the total speed just by squaring those and taking the square root, and you'll find that you get about 45 meters per second. Now you may have had some philosophical thoughts about this, in that clearly these have to be the same, because if you shoot this up at 32 meters per second, it's going to come down and be going 32 meters per second downward in the same place. And so these two boil down to the same problem. And then you ask yourself, wait, this is funny, because I know that change in velocity is equal to acceleration times time, right? And if I dropped it the first time at rest, the change in velocity is equal to 32 meters per second. So why, if I toss it down, does it not get another 32 meters per second? And it's because, of course, it doesn't accelerate for very long because it's going very fast. And this period of time is very short. And so you can see that if the final velocity is, so when you dropped it the first time from 50 meters, it must have taken about 3.2 seconds to hit the ground. But it's moving much faster. And in order to go from 32 meters per second to 45, it's just a little over a second because it's going so fast. Can I throw a 10 kilogram box at 32 meters per second? I don't know. Here I am with my arm like this, and extend my arm, and this thing is moving at 32 meters per second. I think the easiest way to do this is to recognize that my work of my arm, which is the force I put on my arm times delta x, because I know the length of my arm, is going to be equal to the change in kinetic energy, right? Because the work I put in will give it that kinetic energy. And so the force necessary, right, I have to figure out how hard do I have to push this, because I only have this far to push it. Maybe I can push it in with my leg as well to get a little bit further, which is why you see pitchers go like this. They step from back to forward because they're getting extra distance to put that force on the ball. They're giving the ball more kinetic energy. So the force is going to be equal to the change in kinetic energy of the ball divided by delta x of my arm. So this is 1/2 mv squared, and delta x of my arm, I don't know. If I start from here and I go all the way to here, so I've got 1 meter, 2 meters, I don't know, give me 2.5 meters, okay? So that's 2.5 meters. And what is the kinetic energy? 1/2 times 10 times 30 meters per second, 10 kilograms, over 2.5 meters. Oh, better square it because my units wouldn't be right. And so that's 9,000, 4,500 Newton meters. Kilogram meter squared per second squared is a joule. That's the energy it has. And that can also be written as a Newton meter. And I do that because then I want to cancel with the meters, 2.5 meters. Let's say I can get 3 meters, make it easy on me. That means I need 1,500 newtons of force on my arm. Okay, 1,500 newtons is, that's the force of gravity, right? Because force of gravity is equal to mg. So 1,500 newtons, 1,500 newtons is the force of gravity on 150 kilograms. Okay, so my mass is 70 kilograms. So that would mean, could I hold up 2 people in one arm and hold that force? You decide.